So today's topic is subspaces. Yeah. This is 2.8. Actually, this vector space is in 4.1, but we're talking about subspaces. So we're skipping a couple of sections, and our focus today is 2.8. So we're skipping a bunch of, there's a whole section on computer graphics and another one on economics. I was definitely not going to do the econ part. But I thought about doing computer graphics. Oh, speaking of computers, is it you guys? Maybe we might have somebody come up here and talk about dealing with matrices using Python. So we'll see if that happens. Anyways, we're looking at vector spaces. And what is a vector space? So a vector space is a collection of things, a collection of objects, and we're going to call those objects vectors. And they need to have two operations embedded in there. So the two operations are going to be the vector addition and the scalar multiplication. So in talking about vector spaces, there needs to be an understanding about what a scalar is. And then the vectors will be either made up of the scalars or made up of some other object that uses scalars. What? Elements. Well, the vector spaces are, the elements in the vector space are called vectors. And then there's this other extra thing called a scalar that the vectors will be using. And when we start seeing examples, it might be a little bit clearer. Okay. Capital V is the vector space, correct? So it has scalars, and in most cases, we're going to be dealing with real numbers, but if you want to be really generic about this and general about this, it could be complex numbers as well. Or it could even be like a small set of numbers like zeros and ones. If your number is just zeros and ones and you don't have any other numbers that you're dealing with, then those could be the scalars for a specific vector field that we're talking about, or vector space. Okay, so the idea of scalars for us, we'll just stay in the real number world. So aside from the vectors, the vector addition and scalar multiplication, there are 10 things that has to happen. So the axioms must hold these 10 things. And most of them can be named something, or we can put a name to it. The first one, the sum of u and v is going to still be in V. This is to say that it is closed under addition. Closed meaning if I combine these things, then I'm still going to be within my vector space. Now, the second and third one should be obvious. I mean, not obvious, but we should know the names for them. Commutative under addition and associative under addition. And then there's a special vector that has this property where it's the, they call it the additive identity. That's a 0 vector. And then there's a reverse for addition, which we kind of call it subtraction, but technically you're adding a negative number. So this is called the additive inverse. So all these things have to work for addition. So far, pretty straightforward. So far, seems like it's just like the real numbers, right? Okay, now there's this other operation that we're doing in the vector space called scalar multiplication. So closed under scalar multiplication, this says if you scale a vector, if you perform the scalar multiplication, which should be defined, then you're still going to be within your vector space. This is a closure again, closed under scalar multiplication. And then there's a couple of distributive properties that are involved here. And then there's an associative property. What's missing here? What seems to be missing? What? Look at the top part. Look at the first 5. What's B? What? You understand what I'm asking? Yes, there's no commutative. So in this I keep calling it field. In the vector space, the scalars live in what's called a field. Actually, the commutative. It should be fields are commutative. Never mind. Anyways, the commutativity is not important because it's a vector field. It's assumed to be commutative anyways. And there's no commutative property for scalar multiplication. I guess that's what I'm trying to say. And then similar to the additive identity, there's like a multiplicative identity, but it's not just a regular multiplication. It's a scalar multiple identity. Okay. So these things have to exist for this to be a vector space. So let's start off with a vector space that I kind of mentioned before, and then we'll go to the vector space that's super easy and what we're going to be referring to anyways. So let's start the vector space of, yeah. So you're mentioning matrices, but what if we're not talking about matrices? Like the example that I'm going to give is not have anything to do with a matrix. So I think the idea is that we need some sort of scalar, something to scale things with. All right, let's take a look at an example of a vector space. Let's take a look at the vector space of polynomial functions. Sometimes we call it P. Fancy P. I guess you could just use a regular P. I don't know. Figured this might be an opportunity to use a fancy P. So an example of a vector in P, let's say V is a vector in P, could be like x squared plus 2x minus 1 is a polynomial. So that's an element, right? Let's take another vector, x to the fourth minus 3x is another example of a polynomial. So that's an element in P. Because it's a vector space. And so you can call it's an element, right? So it's just called a vector. That's what we call elements in V. In this case, V is equal to P, and then that's what we're going to call it. So elements in that space, in that vector space, is called a vector. So we'll call it a vector. No, that's the thing, is that these vector spaces and subspaces, they don't just have to be from matrices. They could be anything. Or it could be, yeah. Okay? And then we can say we have a scalar 3. That's a scalar. It's a real number. And then we have a scalar d equals -2. That's another. These are scalars. These are vectors. So you can run through all these properties. If you add these two vectors, if you add these two polynomials, you're still going to get a polynomial. Is that right? It's still going to be a polynomial. The polynomials, you can switch the order, or you can associate 3 polynomial functions. Right? There's a 0 vector. 0 is a polynomial. And we can take the negatives of these polynomials, and that's the additive inverse for the polynomials, so that you can get 0. And then you can scalar multiply. You can multiply 3 times one of these vectors. It'll still be a polynomial, right? You can distribute the 3 between the addition, the sum of v and u. And then you can distribute one of these vectors over the sum of c and d. So all these will hold. So because of that, we can call the set of polynomials a vector space. Okay? All right? Is that okay? I was going to do all of them, but that's going to take too much time. So why don't we just move on? Yeah. We'll do something like that when we talk about subspaces. So let's do the vector space that we're all familiar with. R2 is a vector space. We know that, right? So the vectors in R2 look like the vectors that we've been messing around with. And then the scalars are just the real numbers. Okay? So R2 satisfies all these. You can switch to addition. You can re-associate the addition. There exists a negative, the additive inverse, the zero vector, all that other stuff. Okay? Okay? So this is really what they introduce as vector spaces, although in this topic of subspaces, they assume that this is your vector space. But I wanted to tell you that vector spaces are not just restricted to Rn. Any n dimension can be a vector space. Okay? And when we say a vector space over something, the something is technically your scalars, your set of scalars. Do you know what R5 is, or R2? Yeah. Z. Sorry. Yeah.
If it was like R3,
Uh-huh.
could the scalars be exist in like R and R2? Or just
No, just R. Scalars are always just going to be the simplest ones. Yeah. All right. Should we do another strange one, or should we just move on? Strange one. A strange vector space. Okay, so let's say scalars Z5, which is a set of integers. Z is a symbol for integers, and the sub 5 says how many integers you have. And so I have 0, 1, 2, 3, 4. I have 5 elements in this. Okay, so these are your scalars. This is the field that the scalars live in, which means we need to know how to add in here, because if I add these things, I want to remain in this set. Oh, I don't know what I'm doing anymore. Z is a field of scalars, and then I'll eventually create the vector. So I could just be Z sub 5 to the second power as in Z squared. Yes, that's what this field is. So to get anything else, if you're trying to add a couple of things, they have to remain in the field. So if you were to add, let's do that, 3 and 4 equals 7, right? But if you're within this field, I can't have 7. 7 is too big, right? So do you know how to deal with that? If you're a computer science person, you should know about modulus. What's mod mean? So divide by 5 and take the remainder. So 7 divided by 5, and then the remainder is going to be 7 divided by 5 is 1, with a remainder of what? 2. So this is your value. So this is, yeah, you're kind of wrapping around. What? Yeah, it's like the binary system, 0, 1, 0, 1, 0, 1. So 3 is actually 1, and 7 is actually 1, and 15 is actually 1. I need an even number. It's not different. It's the same. You would consider 7 equals 1, 7 equals 2. So you can have a vector field where you're only using these numbers 0, 1, 2, 3, 4, and then you have to go by the same rules as this. So Z2, for example, would be 1 and 4 would be an example of a vector in there. And then U, let's say this has 3 and 2. So that when you add them, V plus U, 1, 4 plus 3, 2, you get 4, 6. But 6 is not one of those numbers, so you need to do that 6 divided by 5 and get the remainder. Okay, so if you follow through the same axioms, addition and scalar multiplication and stuff like that, it should still work. Yeah. The remainder it's called a modulus. So mod, and that means that your remainder is always going to be a number between 0 and 4. If you divide by 5, your remainder is always going to be between 0 and 4. And that's going to be the value that it takes in case you add something and then you go beyond that. It's like the clock. Let's stay from 0 or from 1 to 12, right? If it's 10 o'clock and then you add 4 hours to it, you could say 14 o'clock. But if you look at the clock, it goes back around 4 hours after 10, so that's 2 o'clock. So you're remaining within those 12 digits. Yeah. So Z constrains not constrains, but that's how the field is set up so that when you create a vector space, you're only going to use these numbers. The mod is describing Z sub 5. Yeah. But the vector space would be making vectors out of it. No, the mod has nothing to do with this being a vector space. This is a vector space because now I can use this field to add more things to it. So I can make vectors out of it. The mod business is just a way to do the calculations when you add or multiply. Yeah, I just made them up. They're nothing. Yeah, there's nothing special about these vectors. These vectors are just examples that I'm just coming up with. You can't have decimals for this. So the only things that you can put in the vectors, or the only numbers that you can play with in Z sub 5 is 0, 1, 2, 3, 4. No decimals, nothing bigger than 5, nothing bigger than or equal to 5. Just that. Yeah. So that you're within, yes. Okay. All right. So all these are glimpses to a bunch of different vector fields, but like I said, or vector spaces. But like I said, we're really just focused on R something, Rn. Okay. So that when we talk about subspaces, we're restricted to this, and that's for us easier to see. But in reality, when they talk about vector spaces and subspaces, that can exist in a lot more complicated way than just the vectors as we know it. Whew, that was probably more than we wanted. All right, our main topic is subspaces. So a subspace of a vector space is going to be a smaller subset. It's a subset, but it has to satisfy a few conditions. So here they have 3 properties. More formally, you can expand these properties to like 6 of them or something, but there's 3 general properties. 1, the 0 vector has to be part of the subspace. 2, it has to be closed under addition. And 3, this is a vector space, so the idea of a scalar multiplication is defined. It has to be closed under scalar multiplication. And everything else that we saw in the vector space axioms would hold because this is all under the same thing. Okay. I found some examples in the textbook that I'd like to use, and it's in R2, so we can actually visualize it. So let's take a look at some examples. So these problems, they want us to figure out H is a shaded region. Assume the included, the bounding lines are included. In each case, give specific reasons if H is not a subspace. For instance, find 2 vectors whose sum is not in H or whose scalar multiple is not in H. All right, so let's take a look at that. Yes. So this is your H. So this is your H. Your H is in the first quadrant. Your vector space, this whole thing is R2. So H is a subspace of R2, right? Now let's just make sure that it actually is a subspace. So if we have 2 vectors in here, any random 2 vectors, and if I add those 2 vectors, it has to be, well, first of all, 0 has to be in it. So the first criteria is checked. The 0 vector is in H. So B, if I add these 2 vectors, V and W, or U and V, am I still going to be in H? So use the parallelogram drawing, and then you'd be over here. So this is still in H, right? So now the next one, the last one, is a scalar multiple. If we scale a vector in H, is it still going to be in H? Yeah. Oh, what if you do a negative number? So negative 1 times U. So negative 1 times U. This is U. Negative 1 times U goes back. Now it's not in H anymore. So this is not a subspace. All scalars, in this case, the scalars are all real numbers, and so anything. Oh, because it's you're including the boundaries here. And the 0 vector is right here. That includes the boundary. Okay? So seeing it in a vector space that we're familiar with is pretty easy, especially if it's like R2, maybe even R3. Okay? Yeah. So the next example that they have here is this. This would be a subspace, it would seem like, right? Well, if other higher dimension, you'd be looking at quadrants and octants and what comes after that. So in this particular example, H, the whole thing is H. So H is a subspace. Zeros included, anything we add will be in H, and then scalar multiply, even the negatives can go backwards. We're still going to be in H. Okay? Yeah. Yeah, adding the negative is it's because you can scalar multiply and then add. What's that called when you scalar multiply and add? Well, that's this example right here. This one, yeah, if you can give that to me, you can let me know and then I'll put it up there.
It's going to be the fourth quarter.
What? So if I have here, zero, what? 0, 1 for the y. What's this? So negative 1, 1. Oh, so it might not work, huh? What? Zero, 1, negative 1, 0. Wait, negative 1, 0, 0, 1. And you add them. What's wrong with this logic? Hmm? No, yeah, I guess this is not a subspace. Wow. Okay. All right. Well, doesn't include subspace. You think any of these would work then? You think so? Because if you're over here, the negative. Wow. What good is this? Well, let's see. What are the possible subspaces? Are uh-huh. All right. So what are the possible subspaces in R2? What if we just had the zero vector? Right? So zeros in a zero vector. I mean, zero vectors in zero vector. If I wait, let's talk about this first. So zero is vector space. Let's call this vector space S1, S0. Let's call it S0. Um, so zero is it's closed. I mean, it's in the subspace. If I have two vectors, I only have one vector. So if I add them, it's still going to be zero. This is kind of degenerate. And then C, if I multiply a zero vector by anything, this is equal to zero. That's the subspace. So zero is a subspace. Let's call this S2. I'm going to skip over S1. So S2 would be the whole thing. We looked at some of those examples, and if we only take partitions or parts of it, then we're not seeing anything. So if it was the whole thing, I would just say R2. S2 is equal to R2. And then all these three things would work. 0 is in S2. And if you take any vector, u and v, add them, will be in S2 because it's in R2. And then if you scalar multiply anything, it'll be in S2 because it's the whole thing. So there's a degenerate case and there's the whole case, the whole thing. So now the question is there something in the middle? Yeah. So if we have any vector going through that line, right? So let's call this a vector v. Then anything in the subspace will be v times something, scalar multiple of v. Right? So if we take another vector u, then u and v are scalar multiples of each other. So first of all, since it passes through the origin, 0 vector is in the space. If you add two vectors, u plus v, they're scalar multiples of each other, right? So this is just a scalar multiple of V, and that's in the subspace. And then, of course, a scalar multiple of anything is also. Okay? So these are the only three possible subspaces you have in R2. It's either just 0, it's the whole thing, or the only thing in the middle would be a line passing through the origin. Yes? Not necessarily, but sure. I just made it up like that. Okay? Any questions? Let's find subspaces for R3. So in R3, we'll start again with a 0 vector, right? And then we'll start with the whole, after the 0 vector, the biggest thing would be the whole space. So these are subspaces, the degenerate case and the whole thing. So now let's see if we can find proper subspaces of R3. A one-dimensional case is what? A plane, so that's a two-dimensional case. Plane through origin, and then the one-dimensional case is the line through origin. Okay? Let's take a look at the line through the origin. We have this line going through the origin. What can we say about that line through the origin? How can we relate it to vectors, since we are talking about vector spaces? Or just the vector times the scalar, right? So what does that mean when I say this vector v times a scalar? I guess it might be better if we talk about a plane. Let's talk about H2 real quick, and then we'll come back to this. See if I can draw a plane through the origin. No, it has to be a number. I mean, yes, but it has to be just a number, right? So this plane goes through the origin. What can we say about this plane? I guess I should have drawn this in blue. What can I say about this plane in terms of vectors? There's two vectors. I can imagine two vectors on the plane that are not going in the same direction, right? And then what if I want to find another point in the plane? What can I do with these two vectors? You can scale them and then add them. By scaling, it also includes a negative portion. So alpha times v plus beta times u is still going to be in this space, right? So what can I say about this space in terms of the vector? The space is what in terms of those vectors? Thank you. So H2 is spanned by the vectors v, u, and v. So what can I say about H1? Well, in this case, it only has one vector. Okay? Yeah. Wouldn't it be? Yeah, I think that would be everything. Yeah. So let's see. H1 is a line passing through the origin. It's spanned by one vector. We can say it's a one-dimensional subspace. H2 is a plane through the origin, and it could be spanned by two vectors. H3, the whole thing, you can see that as being spanned by three vectors, and then you can look at 0 as being spanned by no vectors. Okay, so in talking about this, we're kind of building a relationship between the number of vectors that spans that particular space and the dimension of the space. And since we're restricting ourselves to Rn, then there's a specific pattern that happens here. Okay? So now, without pictures, let's try to imagine what happens in R4. We can have the 0 vector. And I need to give it a name, so let's call it S0. S1 can be a vector spanned by one vector, or a space that's spanned by one vector. Alpha is a real number. So equivalently, this is a line passing through the origin. We can take a look at a four-dimensional plane passing through the origin. So that's just two vectors in R4 that spans everything. Now this is kind of like the weird one. I need another Greek letter. This is a Greek letter gamma. And then U, V, and W are vectors in R4. So alpha, beta, gamma are real numbers. And then U, V, and W are vectors. So this is a space passing through the origin. Don't try to visualize it. Just don't. So you have the degenerate case again. You have the whole space, and in between, you have subspaces, proper subspaces, that are either spanned by one vector, two vectors, or three vectors. And we're not saying this explicitly, but those vectors need to be linearly independent from each other. Because if any of those vectors are dependent, then you're losing one of the dimensions, right? If you have two vectors and they're linearly independent, they can span a plane. But if those two vectors are linearly dependent, then you're not spanning a whole plane, you're just restricted to a line. Okay? Any questions? Yes. Yeah. Yeah. So that's the dimensional space that you can look at. That's a proper subspace. Yeah, S and Rn. Yeah, the whole thing. Okay. So these are how you find subspaces. And if you take any portion of it away, like instead of looking at all of R2, if you take any of it away, then it's not complete. It's not going to be your whole subspace. All right. Now there's two very important subspaces when we're dealing with matrices. So the column space and the null space. Column space, I don't have notes for this. I just copy from the book. There we go, column space. So the column space is going to be the linear combination of the subspaces. Now, the dimension of that might be the number of columns that are all linearly independent, but if it's not all linearly independent, then it's going to be a dimension shorter. If it's not linearly independent, then it's going to be a smaller subspace. That seems pretty straightforward, right? And so the other important subspace is a null space. So let me define that, or let the book define it. Then it's the whole vector space, yeah. So the notation we use for column space is COL, and then whatever the matrix is, col A is a column space, and then null, you can add another L here if you want. I mean, it's just one more letter, and it's the same as the last one. So, but they like to use three letters. the null space is going to be the solution to the homogeneous system. Because it's, yeah, 0. It's all the things that get sent to 0. So it's all these vectors over here, all the vector x's that get sent to 0. And we're a little bit out of time, so we won't be able to do an example, but this is what we're going to start with next time. We're going to talk about this in dimensions. So we are in section 2.8. We will do 2.9, and then we'll jump to the next chapter. Yeah. Yeah, I was going to squeeze in a quiz. So be prepared to take a quiz on Wednesday unless I somehow make it a take-home quiz or something. On inverses, finding the inverse of matrices. Random. Let me stop